represented by the senior consultant of Umlaut, SE, and he'll talk about why fuels are how they can be cost competitive. And he gives us an analysis of the fuel cell value chain, right?
That's correct.
Okay.
So this doesn't work now? Okay. Okay, yeah, so here we go. Well, thank you for the kind introduction, and thank you for your time. So for the next 12 minutes, we will talk a bit about the fuel cell, or about a meta-analysis of the fuel cell value chain, and we're trying to shed some insight or some light on the question, why are fuel cells not yet cost competitive? And essentially, this is an accompanying talk or a teaser to a NOW finance study on the fuel cell value chain. And the goal of this study is to basically have a technological description as well as a detailed analysis of the current market for PEM and solid oxide fuel cells. And we will also perform a detailed analysis of the fuel cell components, trying to look at the gap. Why are fuel cells told to be cheap or to become cost competitive, but today they're still not? So for this talk, let's first look at the market. And as of 2020, only about 35,000 vehicles were registered worldwide. The vast majority of them in Asia and the Pacific region. But this market is expected to scale up within this decade to about almost 500,000 registered vehicles by 2025, and about more than a 100-fold increase by the end of the decade. In the short term, this will be driven by the demand increase in Asia and the Pacifics, and then in the long run, the European and North American markets are going to catch up over time. Yet one prerequisite for this is actually that the fuel cells are going to be cost competitive. And I'm sure you all might have heard this for quite some time, that this is the age of the fuel cells, and they're going to take over and they're going to outperform other systems. And yet here we are in the year 2022, and we still have not achieved this point. And hence the question of this talk, why are fuel cells not yet cost competitive? So we tried to tackle this question by breaking down the fuel cell system down to the various individual components. So we first looked at the stack and broke down the stack further down to the bipolar plate, the membrane electrode assembly, and the gas diffusion layers. And then we were looking for studies, scientific studies, which predict the costs. And here we were focusing on studies which were about like 5 years old, because these studies actually predict the costs for today. And then we took those numbers and we tried to validate them by 3 different means. So first, we took the Mirai 1, published cost data on the Mirai 1, which obviously is a bit of an older data set, but it still serves as an upper limit and can give you a sense of where we have been or where we should be at least. And then the second mean, we focused on bottom-up calculations, like the one published by Thompson et al., who performed a very detailed analysis or calculation of the production process of a fuel cell stack, considering, for instance, cycle times and the like. And we also took these numbers and used them as a basis for expert interviews. So we talked to specific actors, players from the fuel cell industries, and asked them for their opinion if those numbers are actually achievable, and if not, what are the main obstacles to overcome. And we did that essentially for all the components you see here, but for the remainder of the talk, I will only focus on 2 aspects, on the stack and on the membrane electrode assembly for now. So what we see here is the normalized production cost for the fuel cell stack as a function of the production volume for different applications and for different years. And what we see at first sight is that already by scaling up the production volume from 1,000 to 20,000 stacks per year, we can actually reduce the manufacturing costs by almost 75%. And when we look further, and when we further increase the production volume to higher numbers, we only have a small influence, and the costs converge towards 9 euros per kilowatt for passenger cars, and towards 23 to 25 euros per kilowatt for trucks. And we also looked at the cost reductions over time, or the projected cost reductions over time, but for the same production volume. And what we see here is that we basically expect a reduction of the manufacturing cost by only about 30%. So let's look at how the cost structure is here for mobile fuel cells. Again, in the top row you see the cost breakdown for passenger cars and for different production volumes, and in the bottom row we have the cost breakdown for the trucks. And what you see in for either application, the membrane electrode assembly is by far the most dominant parameter determining the production cost of the fuel cell. And what we also see that with increasing production volume, also the importance of the membrane electrode assembly on the costs increases. This contrasts, for instance, with the bipolar plate, where the cost share remains fairly constant over the different production volumina for both applications. So how hold those projections up? So we took those numbers, and for the first pillar of our validation, if you will, we see that the production cost of the fuel cell stacks for the Toyota Mirai 1 are actually well within the expected target costs. And also the data from the bottom-up calculation basically confirm the projections. And this is also fairly well in line with what the industry told us. Here we know that for passenger cars, the targeted costs for large volumes are ambitious, but they're achievable. This is a bit different for trucks. Here we actually might have, here it's a bit more challenging, and the costs might actually be a bit higher in the end. So what are the key challenges here? For one, it's still the low production capacities, and particularly linked with the high initial investment required to build up these production capacities. And this is particularly important when considering that, for one, we still have a competition with the build-up for battery electric vehicles, and and we still lack standardization on a component level. So when we now look further at the target cost development of the membrane electrode assembly here, because it makes up for the highest share on the cost structure, we basically see that the MIA has the same manufacturing scale-up potential as the stack. So we see about 30% in savings over time, and about 75% saving by scaling up the production from 1,000 to 20,000 stacks. And the cost will converge towards 5 to 9 euros per kilowatt, or 15 to 20 in case of trucks. And again, when we look at the cost structure here, we see the overarching importance of the material prices, which make up to 90% of the MIA. And particularly when increasing the production volume, this becomes even more grave. Yet when you look at the overall absolute costs, they will go down, which is most likely to be attributed to the cost share of the Nafion, which can actually scale up quite nicely, considering that right now we have a very small market. In contrast, the production for platinum will hardly scale at all. So again, like how do these projections hold up? And here we have a bit of a gap. So even for the Mirai 1, the costs are slightly above the expected target costs, but the data from the bottom-up calculation essentially confirm the projections. And this deviates from what we've learned from our interviews with the industry. And right now, we actually have to calculate with actual costs, which are about 1 order of magnitude higher for very small production volumes. And one issue that we have here is that these projections are basically based on non-state-of-the-art processes. Here in this study, James et al. Used the direct coating of the membrane, which is a very cost-efficient process, yet it regularly produces defective membranes, whereas the currently the state-of-the-art process is the decal process, which comes at high costs because of cost-intensive machinery, which has to be used here. Further, we have the issue that, particularly for the heavy-duty applications, we have to oversize the cells, as we have very high lifetime requirements, and we still have not solved the issue of catalyst deactivation. But this is only the technological side to it. We also have the issue that we have in Germany. We have quite a poor market situation with only few relevant players, and accordingly, pricing is fairly difficult due to a lack of competition. So here, the issue is twofold. To sum this up, for the stack, for the large-scale production, the costs for the passenger cars are most likely achievable, whereas it might be a bit difficult for the trucks. The main challenge here is to achieve standardization, some degree of standardization to achieve economies of scale. For the MIA, we have technological issues, but we also have a defective supply chain. So here we actually have 2 handles to reduce the costs by creating competition and optimizing the supply chain. And this differs a bit to the bipolar plate, for instance, where we have a very competitive market in Germany, and here the main challenge is rather in the high investment costs required to build up production capacity. But right now we actually see quite some action going into that direction. And with that, I'm open to questions. Please.
Just wait.
Hi, thank you very much. I did read quite a lot about hydrogen fuel on the internet. Do you think, because I did not see that issue on your slide, do you think that the production of hydrogen fuel will generate a lot of carbon dioxide, and that could be a major issue as well, on top of all the challenges that you have already stated?
So I couldn't quite get your question because it's a bit too not
so
loud
my
enough.
questions to you is, do you think that the carbon dioxide emission issue could be also one of the major issues to this technology?
The carbon dioxide emissions?
Yeah, exactly.
And the production of fuel cells?
The production process of the hydrogen fuel.
Of the hydrogen fuel, well, it should be green hydrogen, right? So hydrogen produced by electrolysis and not by, for instance, cracking of any hydrocarbon, if that's what you're referring to.
Maybe
at least that's the policy in Germany, right? If you want to get funding, it has to be green hydrogen, not gray hydrogen or blue hydrogen.
Because basically right now the problem is that, yes, in general, hydrogen could be a very green energy, but in terms of the manufacturing process, I mean, for the oil and gas industry and so on, this has been a point that has been tackled by the automotive industry. Do you understand what I mean? That's the reason why nowadays everybody talks about electric cars, but not hydrogen cars, because there's a big loop that has not been resolved. But I do not. Do you think that you understand my questions correctly, or do you have the answers for me today?
I'm not sure if I got your question right. I think you might actually be referring to life cycle analysis of the production of the fuels, which has been not in the scope of this study. All I can tell you is you can, well, as long as the hydrogen is green, you'll have a clean fuel. If the energy mix is not green, then the hydrogen you produce is definitely not green, if that's of any help.
Okay, thanks a lot, Dr. Jan Ilsemann. If you have some more questions, you can find him in the other hall. Are you there every day?
No, just today.
Just today. Today you can find him. How long? 1 hour? If you have some more questions.
Yeah, about an hour, maybe
It's
two.
hall 5A